Hi, in this video we will look at the motion of an object on an inclined plane. The plane will have a rough surface. Essentially, we will be looking at resolving all the forces acting on the object. Here's the first possibility. The object remains stationary because all the net forces are balanced. That means they are in equilibrium. And that means, of course, that there will be zero acceleration and either zero or constant speed for the object. Another possibility is that depending on the net forces acting on the object, there will be positive acceleration uphill, and that will mean increasing speed. Something like that. And the third possibility is that the net forces will make the object move downhill, and that will mean again positive acceleration and increasing speed. So now let's look at the net forces acting on the object. Let's assume that the mass remains stationary. There's our inclined plane at an angle theta to the horizontal. Mass m kilogram. First of all, the unit of force is the Newton, where 1 kilogram weight is the same as 9.8 Newton, which is really the gravitational force on a 1 kilogram object. And we represent the gravitational acceleration g as approximately 9.8 meters per second squared. So one force that acts on the object of mass m is a vertical force acting downward of magnitude mg. Another force, because we have a rough surface, there is a frictional force acting upwards, up the plane, which we will label as F. We also have a reaction force of the surface to the object, and we normally refer to that as N, and it's vertical to the plane. And there is one other force. Can you guess what it is? To find out the other forces, we will resolve the forces parallel to the plane. That means in the same direction. And to do that, if you look at the diagram, I've created a right angle triangle in those dotted red lines. Angle theta, same as the angle of the inclination of the plane to the horizontal. The parallel to the plane force is that one. There's F, our frictional force, acting upwards, and the other component parallel to the plane is the one that is labelled mg sine theta. And of course, since the object is in equilibrium, the forces in the parallel direction, parallel to the plane, balance. So we can write that F minus mg sine theta equals 0. Similarly, we can resolve the forces vertical to the plane. There they are, shown in green. And the reaction force is one of them. And opposite to that is the adjacent side of the triangle to the angle, which is mg cos theta. And of course, they are also equal and opposite, so we can write that n minus mg cos theta equals 0. Let's label those two resultant forces 1 and 2. Now from equation 1, we can rearrange that to get F equals mg sine theta. And from 2, we can write n equals mg cos theta. So let's refer to those two equations as 3 and 4. If we divide equation 3 by equation 4, we have F divided by n equals mg sine theta divided by mg cos theta. The quantities m and g cancel, and sine theta divided by cos theta is a trigonometric identity, which is tan theta. So we have F over n equals tan theta, or we can write it as F equals n tan theta. In other words, the frictional force is the same as the reaction force multiplied by the tangent tan theta of the angle. Now it turns out that the property of the roughness of the surface, which we call the coefficient of friction and represented by mu, is equal to tan theta. So that means we can replace our tan theta by mu, and we have F equals mu n. But we also know from equation 2 that n is mg cos theta, so we can write that the frictional force is equal to mu mg cos theta. Now let's look at the situation where the mass actually ends up moving uphill. For that to happen, the net force, the resultant force, must be in the upward direction, parallel to the plane. So again, resolving forces parallel to the plane, the net force will be the applied force minus the frictional force acting down the plane, and then minus the component parallel down the plane, which is mg sine theta. Now, from Newton's second law of motion, we have that the net force, the resultant force, is mass times acceleration. Now, our net force is shown above, of course, A minus F minus mg sine theta. So we can write what we have there. Mass times acceleration is m times A for acceleration. And we also know that F is the frictional force, which is mu mg cos theta. So we now have an expression for ma, the mass times the acceleration. If the acceleration is 0, we can have constant speed or 0 speed, of course. But more interesting is when the acceleration is positive or greater than 0. And that means that, rearranging the equation to make A the subject, we have the acceleration equal to 1 over m multiplied by the expression that we have there in brackets. In a similar way, we can look at what happens when the mass moves downhill. There's our diagram. We have our frictional force working against the motion, in this case uphill because the object is moving downhill. We have an applied force downhill. We have our reaction force again, of course, and our gravitational force. So our net force acting downhill would be the applied force plus the component of the gravitational force acting down the slope, which is mg sine theta, and then minus the frictional force. And of course, using Newton's second law of motion again, we have that is equal to mass times acceleration. And substituting for our frictional force, F being mu mg cos theta, we have our expression, and then to get acceleration, divide both sides by m. Again, one possibility is that the acceleration is 0, and that of course gives us constant or 0 speed, but we said the object is moving downhill, so that means the acceleration will be positive. And again, if we divide both sides by m, there's the expression we have. So we have two expressions for the acceleration, uphill and one for downhill. Let's try an actual example. In this case, we will look at the case where the car is moving uphill. Let's suppose we have a car of mass 2,000 kilogram and the engine exerts a force of 20,000 newtons as the car moves up the hill, and the hill has a gradient of 20 degrees. And we are also told that the road surface, which is rough, has a coefficient of friction of 0.4. By the way, coefficient of friction is dimensionless. And from that, we will establish the acceleration of the car. Here's our diagram for the car moving uphill. As before, we have the applied force, we have the frictional force acting downward, reaction force, and the gravitational force. The acceleration that we obtained earlier for the motion up the hill is shown. We will now substitute our known values. The applied force is 20,000 newtons. The mass of the car is 2,000 kilogram. The gravitational acceleration is 9.8 meters per second squared. The angle of the sloping plane to the horizontal is 20 degrees, and the coefficient of friction is 0.4. Making those substitutions into our expression for the acceleration, you can see what we have there, and with a calculator, we will obtain a value of approximately 2.96 meters per second squared. So the acceleration of the car up the sloping surface is about 3 meters per second squared. That means that each second the speed of the car increases by about 3 meters per second. I hope this has given you some idea of how you can go about resolving forces acting parallel and perpendicular to the plane. Until next time, bye bye.